Hello, welcome to Mrs. T's Chem Talk, Regents Review. This last video on the reference tables will be about a section of the periodic table that I realized I left off of the other one, as well as tables S and T. So looking just back at the periodic table quickly, one of the things that I left off of the last video is the locations of things. I did go over on the page about the key. I did go over the locations of the different items, but I didn't talk about how we can use the periodic table to learn something about the electron configuration or the number of valence electrons for elements. So for example, we said that the electron configuration is underneath the atomic number, and we said that the members of the same group or family are in the same column. So for example, this group right here from lithium down to francium is called the alkali metals. And if we look at all of the members of the alkali metal group, what we can see is that each member has one valence electron. So they each have the last number in their configuration is going to for each of them be a 1. In group 1, they tend to have 1 valence electron. In group 2, they tend to have 2 valence electrons. In group 13, 3 valence electrons. In 14, 4 valence electrons. 15 is 5, 16 is 6, 17 is 7, and 18 is 8 with the exception of helium, because remember, helium only has one shell, one principal energy level. So since helium only has one principal energy level, helium is stable with a duet, where neon and the rest of the noble gases are stable with their octet. So these have a stable number of 8 valence electrons, where helium, who only has one shell of electrons, has a stable duet of electrons. We also can use the periodic table to determine something about the ground state electron configuration, because remember that the electron configurations on the periodic table all represent the lowest possible energy configuration, which means that these configurations are all ground state configurations. For an excited state configuration for an atom, it would have to have the same total number of electrons, but at least one electron would have to move to a higher energy level. We can also use the period number to determine the number of total shells. Every element that's in period 1, which would be hydrogen and helium, has one shell or one principal energy level for electrons or containing electrons in the ground state. Everybody in period 2, lithium all the way across to neon, they have a total of 2 shells of electrons that are occupied with electrons, and we can tell that by looking at the fact that they have 2 numbers in their configuration. Remember, each number in the configuration tells us how many electrons are in each shell. The first number in the configuration is the shell closest to the nucleus. That's the shell with the most energy. And as we get further and further out in the configuration, we're showing electrons that are further away from the nucleus and have more and more energy. So the number of the period tells us the number of shells, and also tells us which shell the valence electrons are contained in. We can also look at our selected oxidation states for an element, and we can write our crisscross formulas. So for example, if we want to write the formula for magnesium chloride, we're going to look up magnesium's oxidation number, which is a +2. We're going to use IDE, remember, means that we're going to use chlorine's negative oxidation number. So chlorine there has a -1. We're going to crisscross and drop the signs and get MgCl2 as our formula for magnesium chloride, which would mean that there is 1 Mg, or magnesium ion, with a +2 charge, and there are 2 chloride ions. Sorry if you can see the -1 there. And the 2 chloride ions each have a -1 charge, and this would be the method of writing the ionic compound dot diagram. Notice if you can't see over here, there's a -1 charge outside the brackets. So that was what I missed on the periodic table. So let's move on to table S. Looking at table S, we have a large amount of information, and there are actually 2 pages for table S. And the first page looks like this, and it goes from elements 1 to 40. The second page actually has the same information, except that it goes from 41 to 89. And something of note is that 58 to 71 elements have been omitted, and 90 and above have been omitted. So there is no information on table S for 58 to 71 or for 90 and above. Going back to the front page of table S, some of the pieces of information that you can find on table S, you can find atomic numbers, which if you look something up by symbol or by name, finding the atomic number can help you to locate it on the periodic table if you're having trouble finding it. So for example, if you have to look up something about calcium on the periodic table and you're not sure where to find it on the periodic table, you can scan for calcium here and look up the atomic number and then find the atomic number on the periodic table, since on the periodic table everything is arranged by atomic number. So besides atomic number, symbol, and name, we also have first ionization energy, electronegativity values, melting points, boiling points, densities, and atomic radius values for any of the elements that show up here. So let's just discuss a little bit what each of these are referring to. If we talk first about first ionization energy, first ionization energy refers to the amount of energy required to remove the most loosely bound electron from an atom. Okay, so we're going to remove the most loosely bound electron using the first ionization energy. And so if a question asks you which of the following takes the most energy to remove the most loosely bound electron, or which takes the least energy to have the most loosely bound electron removed, that would be first ionization energy that you're going to look up, and you would find it directly on table S. Electronegativity is going to measure the strength of pull or strength of attraction for or on the electrons in a bond. So electronegativity is measured relative to fluorine. Fluorine has the highest electronegativity at 4.0, and francium has the lowest, and I believe that's at 0.7. But either way, francium is going to have the lowest and fluorine will have the highest. Let's see. We've looked down for francium. Yes, francium is 0.7 as the lowest electronegativity. We also have values for melting point, which, remember, melting point, these are in kelvins. So if we need to convert to Celsius, we're going to use the formula Kelvin equals degrees Celsius plus 273. And remember that the melting point, sorry about that, is also going to be the same temperature that something will freeze at. So that's also, if they ask you for the freezing point, you're looking up melting point, because remember that on the heating curve, if this is solid, this is liquid, and this is gas, melting happens when it's endothermic, freezing happens when it's exothermic, but it's at the same temperature. We also have boiling point. So boiling point is the temperature that it will boil, but it's also the temperature that it will condense, because of the fact that, again, on the heating curve, the boiling and condensing happen. Boiling happens when you're adding heat. Condensing happens at the same temperature when you're removing heat. Density in grams per centimeter cubed is available here. Sometimes questions will ask to compare densities and we think, oh, well, I must just have to guess on this question. Absolutely not. You would look on table S. And atomic radius is here as well. Remember, atomic radius is defined as half the distance between adjacent nuclei because we don't actually know, or it's very difficult for us to determine how far out the electron cloud goes out here. So if we instead measure the distance between the nuclei and cut it in half, that indirectly gives us a way to measure the radius of the individual atoms. If we move forward now to table T, on table T we have a bunch of formulas. Some of these formulas you may just know, you may not need to look up on table T, but just know that they're here. Remember that density formula is here. Anytime they ask you for density, you can use it here. Number of moles being given mass over gram formula mass is here. We can also remember use this to find a mass for a given number of moles if we plug in X as the given mass. Percent error is one that we often forget is here, where we will do the measured value minus the accepted value and always put the accepted value on the bottom. This number up on the top here we usually use as absolute value. So we don't have to worry about which one to subtract. We're just taking a straight difference between the two. We have multiple, we're up to percent composition. We're talking about percent composition by mass. Usually this is the mass on the mass of whole on the bottom is usually the gram formula mass. This is the one where we find the mass percent composition by mass of a certain substance in a formula. And if we, for example, wanted to find the percent composition by mass of sodium in NaCl, we would take the mass on the table of Na and multiply it by 1. We'd take the mass on the table of Cl and multiply it by 1 and add the two together to get the gram formula mass. If we wanted the percent of sodium in that, we would take the mass of the sodium, put it over the gram formula mass, and then multiply by 100 to get the percent composition of sodium. Concentration, we can use parts per million or molarity also. Parts per million is, again, it's mass of solute over mass of solution times 1 million, or simply mass of part over mass of whole times 1 million. We usually abbreviate parts per million as ppm. We can also do concentration in molarity. And if we're talking about molarity, a lot of times this is in the acid-base unit. This is concentration again. Molarity is capital M, and sometimes we will write it, or we have written in the past like this, and you may need to use the mole calculation formula to get the number of moles if you're given grams. You may need to go from milliliters to liters for the volume at the bottom there. For the combined gas law, P1 V1 over T1 equals P2 V2 over T2. A lot of times we're going to use this formula if they talk about obviously pressures, volumes, and temperatures for gases and calculating final pressure or final volume or final temperature. These temperatures always have to be in Kelvin. So you may have to use this formula at the bottom. And as we said in the first video on this, on table A, we have the values for STP. So if they tell you that a pressure or a volume is in, switches to STP, we're going to look at table A to plug those in. And if they tell you that a value is constant, we're just, let's say they say pressure is constant, we're just going to cross it out of the formula and use what's left. Titration, a lot of times a keyword in titration is that they'll use the word neutralized. So a certain amount of acid is completely neutralized by a certain amount of base. That would be when we use MAVA equals MBVB, and we're going to put the molarity of the acid times the volume of the acid, set equal to the molarity of the base times the volume of the base. So if we had, for example, 1.0 molar HCl, and it was neutralized by 2.0 molar NaOH, and it took 25.0 milliliters, my molarity of my acid would be 1.0, volume of acid would be X, molarity of base would be 2.0, and my volume of base would be 25.0, and I'd solve for X. For my heat problems, remember on table B, we have the C value, we have the heat of fusion value, and the heat of vaporization value. We're going to use the Q equals MC delta T when there is a temperature change, and HF and HV are for phase changes. Q equals MHF is whenever we're going from solid to liquid or liquid to solid, and Q equals MHV is when we go from liquid to gas or from gas to liquid. There is no temperature change during a phase change, so if they give you a temperature in a phase change question, it's just a decoy, a number that you don't need to use. And finally, our Kelvin equals Celsius plus 273. If you ever need to go from Celsius to Kelvin or from Kelvin to Celsius, you're going to plug into this formula, and you will always need to do this if you start with a Celsius temperature in P1 V1 over T1 equals P2 V2 over T2, because we can only use kelvins in that formula. So this is the end of the reference table Regents review for Mrs. T's Chem Talk. Hopefully this was very helpful, and good luck and happy studying.